Now we're faced with an open interval, and we would like to find not only the absolute extreme values, but also any local or relative extreme values and the behavior of the function, increasing and decreasing. So we're moving toward fully analyzing a function. In this first case, we have the function x times the natural log of x. We first need to find the critical points of the function still, and the opportunities for this function to have extreme values will happen where the first derivative equals 0 or is not defined. So again, we have a product, f prime g plus f g prime. That cleans up to be the natural log of x plus 1. We care where this equals 0 or where the first derivative is undefined or does not exist. So to solve where it equals to 0, we'd say that this is when the natural log of x equals -1. Then we have to break the x out of the natural log, and we do that with the exponential. So raise each side as a power of e. They undo each other. On the left-hand side, they cancel. E to the natural log is the same thing as just plain old x. And on the right-hand side, we have e to the -1, also known as 1 over e. Now that's a critical point. And then we concern ourselves with the idea of where the first derivative doesn't exist, and that happens anytime a denominator is 0 or we're outside the domain of the function. So either you recognize the limited domain of natural log now, or perhaps you don't, which is a little bit more likely. And we'll explore what happens in that case now. Step 2 was to cut up the interval, or the domain of the function. Let's assume or pretend that we didn't recognize the restriction. We want to go from -infinity to infinity. We have one critical point at 1 over e. That's the only point we mark on the number line. That is the point we want to test for a change in behavior on any side. So on the left-hand side, left of 1 over e, we'll test a value, and I like to test 0. Right, wouldn't you? It's a nice little number down there. So this is step 3, test, and we'll be testing the first derivative f prime, which is the natural log of x plus 1. So if I'm going to test a point 0, left of 1 over e, I would have the natural log of 0 plus 1 and get an error back. We cannot find the natural log of 0. That's because the natural log of 0 doesn't happen. So right here where we tested 0, we get a problem. The first derivative didn't happen there. That's because the original function doesn't happen there either. And that might be the opportunity you have to say, oh yikes, the domain is limited. Nothing happens for us until we get to 0. So we have to pick a different value between 0 and 1 over e. To do that, I need to approximate for myself how much 1 over e is really worth. Uh, 0.36. So some number between 0 and 1 over e would be a number like, maybe I test 0.1. So the natural log of 0.1 plus 1, and I really just care if it's positive or negative. So since it's out, natural log of 0.1 plus 1 is a negative value, -1.3. That means that this function is decreasing on the interval from 0 to 1 over e. Now on the right side of 1 over e, anything larger than 0.36, I like to test a value. So I'll test 1. The natural log of 1 plus 1 equals 1. That's because the natural log of 1 is 0. That's plus 1, we get a positive 1. That means that the function is increasing after 1 over e. So that was step 3. The fourth step is just to decide what's actually going on here. In part A, we're asked for where the function is increasing and decreasing. And then in part B, we would like to know any local and absolute extreme values. So let's do the absolute max and the absolute min. a relative max and a relative minimum. And analyze our little depiction over here. So first we realized that the function was increasing from 1 over e to infinity, and that's indicated by the fact that the test point we used in the first derivative on this interval was positive, and in fact any point we used in the first derivative between 1 over e and infinity would still be positive. If we use 6 or 12 or pi, we would still get a positive value because the tangent lines there have positive slope, which means that the function's increasing. Between 0 and 1 over e, we found tangent lines with negative slopes. That's because we tested one point. We tested point 1. You could test point 2 or point 3, anything less than 0.36, and you would find that all those points had negative slopes of tangent lines. So that means it was decreasing on that interval. Now for an absolute maximum, we might look at this curve and think if there's an opportunity for us to get to a maximum value, and there's not, because this value will just keep on increasing all the way to infinity, growth without bounds. So there's no opportunity to have an absolute maximum on an open interval like this, in this case. But then we do have an absolute minimum. That's because the function came from up high, comes down until we get to 1 over e, and then it turns around and goes back up. So an absolute minimum happens at the point x equals 1 over e, because there's no way for the function to get any lower than that point. For the same reasons we don't have an absolute maximum, there's no relative maximum either. No point where we were increasing and then decreasing. And the relative min, you could say the relative min is also at a point x equals 1 over e, because any absolute minimum would also have to be a relative minimum. He's smaller than his neighborhood. Or I'm okay if you would like to just say none, because we already used 1 over e as an absolute minimum, so obviously he's a minimum, and there's no reason to list him twice. I understand both reasons, so just make sure that you get this one for sure, the absolute minimum, and then whether you choose to list him as also relative minimum or say none, either one of those would be correct.